my name is Eduardo Solano. I'm beamline scientist at the scattering beamline. And I really appreciate that Alexander was first because he did most of the job that I have to do here. So a bit of introduction about the scattering technique. Then I will go through the beamline itself. You will see it later this afternoon, so I'm not going to really lose time on this. And since you are coming from different fields, I will try to give you some overview of what we can do at the beamline, different type of experiments, different kind of setups, and different kind of information that we can obtain. So let's start with the small angle X-ray scattering. Yeah, here Alexander already explained you what is diffraction, so I'm not going to lose time on this. So here you have the detector, the area detector, you have the beam stop, and you can obtain different kind of diffraction patterns. Perfect. But time ago, they realized that behind the beam stop there was some information that was hidden. So what they did, they just put the detector and the beam stop farther from the sample position, and they obtained a different kind of information. So this is what is called small angle X-ray scattering for getting different sample information. While the diffraction, typically in our field, is called WAX, wide angle X-ray scattering, because we are recording wide angle scattering patterns. So what is NCD beamline? So NCD beamline is the SAX WAX beamline, which provides information about the difference on the electronic density in the material. I will repeat this term during the presentation. So we need electronic density contrast. This is really important. You have to keep this in mind if you want to do any kind of experiment. And this, of course, can be combined with the diffraction. You will see how. And this is, sorry, the opposite way here. So this can be combined with wide-angle X-ray scattering by putting a first detector near the sample and the second detector really far from the sample. Perfect. So, as I mentioned, SAX is caused by differences on the electronic density contrast of the material. So you can see here in this nice picture. This is always funny, and this I always put it in the presentations, because you can really see the man here while the woman is sitting down. So it's really easy to see something if you have a different electronic contrast. In the same thing here, we have the Pink Panther behind this. But if we don't have any contrast, we cannot see it. But if we increase this electronic contrast, we can see it. So this is something that is really illustrative of what we need. And there is a principle in SAX that is called the Babinet's principle, that if you have vacuum and one sphere in the middle, you have the same pattern that if you have the same material with a vacuum in the middle. So you will obtain the same kind of scattering pattern. What kind of information we can obtain? Similar like Alexander presented. So if we have the 2D image here, we can reduce to 1D, but of course we are losing some information. We are getting reading out of the orientation information. But this is what most of people do because they are working with powder, they are working with liquids. So we are reducing the data from 2D to 1D. And here we can obtain different information than with powder diffraction. We can obtain information about larger things between 1 and 300 nanometers for SAX. In our case, in our beamline, of course, there are beamline that they are working with ultra SAX, so they can go to micron size. But in our case, it's between 1 and 300 nanometers because we can go, you will see later this afternoon, from a sample detector position of around 2 meters to 7 meters. And we obtain information about, for instance, the interparticle distance. So if we have a dispersion of particles, we can see how they are far from each other. We can also get information about the form of the particle, if we have spheres, if we have plates, or what we have. This is really interesting for biology and for the proteins, right? We can see the size of the particle, how the surface is. So if it's a rougher surface, if we have a porous surface, or how the surface is. And if we go to higher scattering angles, of course, we enter into the diffraction pattern that we already saw before. But why do we need SAX? Because this is the most important question. Why do we need it? I can see these things with a TEM, right? But while with transmission electron microscopy that we have all in the lab, so it's really easy to get access not to a synchrotron, we can get information about the real space, which is easier to understand, of course, because you see the image, with high resolution for small details, and you are analyzing a small area. But this has a problem, because maybe you were really lucky, you went into your material with the TEM, and you got a part of the material that is really nice, really perfect. Then you take this, you publish it, and then the referees ask you, can you do SAX, please? Because with SAX, you will prove that this is statistically relevant for your material. So you cannot trust always on the TEM. You have to go to SACS. Why? Because even if we are working with the reciprocal space, that is making things complicated, and we have a lower resolution, we are analyzing a large volume of the sample. So we have more information about the totality of our sample. But if we want to go to, if we want to have small details, we have to go to TM. If we have to prove our material, we should go to small angle scattering. And we have one advantage here, that it's SACS is a photon-in, photon-out technique. So we put photons, they are scattered by the sample, and they go out. This is perfect for in situ applications because, in fact, we can do whatever we want with our sample while we are recording the scattering patterns. Also, this is very interesting because if we are going through the sample, we don't need to prepare the sample. Of course, we have to be transparent to the X-rays. We cannot put a sample of 1 centimeter or 1 meter because, of course, we will absorb all the X-rays. But we can do most of the in situ conditions that you can imagine. We can apply magnetic fields, electrical fields, temperature, we can stress the sample, we can deposit materials, we can do almost whatever you think. Up to now, I have been talking about transmission techniques, but just to give you an overview that we can also work with grazing incident techniques like GSACS and GWACS, that this is giving us information about the surface of our materials. GSACS is giving us information about the morphology of the surface, if we have nanoparticles, if we have a polymer, or if we have a structure. And GWACS is like the surface diffraction technique, so it's giving us information about the crystalline structure of our material. We will see examples about these two techniques also later, but I want to mention that the same beamline can work in both configurations, and most of the beamlines for scattering can work in these configurations. So let's go to see a bit about our beamline. So I don't have a fancier plot like Alexander had before, but this is briefly what we have. We have an in-vacuum undulator as a source. Then we have the X-rays that are tuned to with a channel cut for an energy range, working energy range of our beamline between 6 and 20 kiloelectron volts. I will explain you later why we have these constraints. And then if we want to see how our X-rays are scattered by our sample, we need to have a collimated beam. Because of that, we have the beryllium collimated lenses, but we have also a possibility to microfocus the X-rays. Then on the sample position, we can see with an on-axis camera, which is a mirror with a hole in the middle that the beam can pass through, but we can see exactly where our beam is hitting, and you can see the zoom level that we can have. So we can correlate the reciprocal space and the real space imaging at the same time. And then we have the wax detector, which is close to the sample, and the SACS detector that I mentioned to you that can go from 1.75 meters to 7.2 meters, more or less. And why we have this energy range? Because if you think the silicon 111 monochrome can be higher and lower in energies, is because we are losing the efficiency of the detectors that we are using in our beamline. So this is a sketch of the experimental station. So the beam is coming from here. We have here the sample position. This is the wax detector, and this is the long fly tube. Okay, and this is the SACS detector here. So we can put the SACS detector, as I mentioned to you, at different positions depending on the region that you are interested. So here you can even have continuity of the reciprocal space. We can measure with SACS, and we can overlap with wax, so we have a continuous spectrum. This is what the detectors looks like. This is the, where is the here. This is the wax detector, and the SACS detector is behind this long fly tube. And we have the Pilatus 1M detector that most of the beamlines for scattering they have now. And for the wax detector, we have another kind of detector coming from Rayonics with a smaller, with a different, smaller area detector, but with a smaller pixel size, so we have higher resolution for diffraction. And of course, we can put the sample on top of this motor tower, that is this one, so we can move the sample up and down, left, right, we can rotate, we can tilt, we can do whatever we want to the sample. And we have different holders to put the sample on. So for instance, we have for ex situ samples, we can put multi-film samples, multi-sample holder. for capillaries, because the liquids should go into a capillary. This is for surfaces, like you have silicon wafers with different materials on top. We can put several of them here. And this is to rotate the sample 360 degrees if we want to have more angular resolution. And for in situ experiments, we have different Lincoln stages, couple for capillaries or for films or for grazing incidence mode. We can have a stretcher to stretch the sample at the same time that we are heating it up, and we can record the scattering pattern. We have solvent annealing systems. We have a shear cell that I don't have a picture now. And we recently have a new gas system infrastructure to expose our sample to different gases and different conditions. So we are working more into the catalysis field. So now I'm going to explain a bit about different examples, and maybe you can think on something for you for the future or in your field, so we can have an overview, and later maybe during the beamline visit or during these days we can, of course, discuss. But first is something that we need to know is when the people come here, they ask me how the sample should look like if I want to come here. How should I prepare the sample? As I told you, you don't need much sample preparation, but of course, if you want to do sax or wax, your samples must be transparent to the X-rays, otherwise you are blocking the beam, so you have nothing. The liquid samples are generally contained into borosilicate capillaries from 1 to 2 millimeters, and we need a minimum sample concentration of several milligrams milliliter, and this allows us to do a lot of in situ experiments. And for the surface science experiments, GSAX and GWAX, that are measured in reflection mode, we need a minimum surface roughness. Of course, if we want to see how the X-rays are scattered on the surface, we cannot have a rough surface, otherwise we wouldn't see the nanoparticles on top or the polymer on top or whatever the material we have on the surface. So it should be a flat surface, because if we have to set an incident angle to see, it cannot be a round surface. And the typical size is like 1 square centimeter. The shorter, the better. This is true. This is totally true. But we should have enough material to see the signal, otherwise we are blind. And this is the same. We can apply this for different materials and different kind of conditions, like temperature. We can study nucleation, growth, crystallization. So these are different kind of fields that we can work with: nanoparticles, thin films, liquid crystals, porous materials, polymers, and gels. That is really an important field of industrial visitors at the beamline, and also fibers. So let's go to see different examples. So this is more, I divided, by the way, in 4 kind of topics. Like the first one is biostructures. So here, this is to investigate how the microtubules are stable with the exposure to different drugs. In this case, they discovered that the taxanes can modulate the material properties of the microtubules, making them much more stable. And this you can do it in situ. So you have the liquid with the microtubules, you see them, you inject the drug by a remote system, of course, you cannot be inside while this is working, and then you see if the microtubules structure is changing or not. This is a second example that is with bacterial nanocellulose, that here you can see it, that they can tune the bacteria to fabricate this nanocellulose in an oriented way or an isotropic way. So you can decide how you want to produce your nanocellulose by changing the approach with the bacterials. And here you see the SAX pattern. This is what I mentioned to you before. If you transform this to 1D spectra, you are losing the orientation information. So here we have to work with the 2D images. Here is a circle, so there is no preferential orientation, while here you can see that there are some elongation of the scattering signal. Here there is another interesting topic, which are the 3D printers. That is really interesting for polymers and things like that. So here you can see that at the beamline, the users brought their own 3D printer. They installed it on top. You will see a picture later. And we could analyze how the polymer looks like at different points of the wire that we are producing, that we are injecting. Depending on the conditions, like the temperature, the velocity, the kind of polymer, we can investigate how this is crystallizing, if it's more oriented, less oriented, and this has an effect at the end on the properties of the material. So this is really critical for industrial applications. So here another example, which is very nice, that is very basic fundamental application, but has a really industrial relevant, and is really important for industry. Because here we had a polymer on a liquid, we put a plant on it, and then the polymer was starting to grow on the roots of the plant. perfect because we have a hybrid system, a bioplant, a biosystem with a biopolymer, which is covering the root of the plant, but that we can use to grow the polymer, and at the end can be used to store energy or act as an electronic sensor. So this is very, very interesting. And what we did with GWAX in this case, so raising wide angle scattering, was to investigate how the polymer looks like into the root. So you can see the roots here. You can see that these are few microns, so we were able to analyze the polymer on this root. More for catalysis, in case that you are in the field of catalysis. A couple of examples. Here was water oxidation electrocatalysis using ruthenium coordination oligomers. So the chemistry and the simulations predicted that the oligomers should look like this on the sample surface. So with GWAX, we were able to see that we had this nice orientation of this structure on the surface. So we were able to prove that the theory and all the models and all the basic of the structure of this paper was correct. And here we have another example of polymer microparticles that were mixed with iron oxide nanoparticles, magnetic particles, and with enzymes for catalysis. And they wanted to see if by mixing this with the magnetic nanoparticles, they were changing the structure of the polymer and the enzymes. And they realized that no. So they can do like a hybrid polymer magnetic nanoparticles, microparticles for enzymatic catalysis. And then a couple of examples more to finish. This one I won't explain because Klaus already explained. It's for organic bipolar transistors. And the idea was here to have for optoelectronic devices more on the soft materials range, but here this is for high materials range. So this is a perovskite, and as you may know, the perovskites are really promising, but they are not stable under normal conditions, especially against humidity. So here we were able to investigate how this structure looks like when we trap this black phase, that is the active and nice phase, thanks to the substrate preferential orientation. So we were able to investigate this, and it's very nice and very clear example how you can keep one phase, and you can see this kind of patterns. And the moment that you, for instance, you close the nitrogen or you expose it to water, you can see this how is it changing. So by understanding how is it changing, you can do different things to prevent this. And at the end, we were able to stabilize this black phase at room temperatures and normal conditions. But we are doing more things at the beamline. So this is the take-home message. We can do almost whatever you want to do. And to be honest, I never believed that we can do so many things when I start with this field. Because here you can see, you know, the spin coaters that we have in the lab, we can do it in situ, spin coating in situ. Here is to make sure the conductivity in situ. So you can see the conductivity changing while you are changing the scattering pattern. Here is for catalysis. Sample exposed to different gases at different temperatures and see how it's changing. This is the 3D printer. This is for batteries. This is a homemade battery cell, large enough to work comfortably, but this is like that. This is a really relevant investigation for industry, but was a research group that working with companies, because this is a machine that is used in real companies to produce polymers from pellets. So you inject the pellets here, and then you collect the roll of polymer here. So with SAX and WAX and GWAX, we were able to get information of the polymer all along the production chain. So this was very, very nice. And this is atomic layer deposition system, or this is a superconducting material growth system. So we can do a lot of things. So just to summarize, the NCD SWEET beamline or any scattering beamline can provide information about the scatters between 1 and 300 nanometers for SAX, and for GWAX can provide structural information below 1 nanometer more in the crystalline structure range. And we are working in these 4 main fields, but of course we are open to work with different fields. So now up to here my presentation. So if you have any doubt or any comment, we can discuss it now or later during coffee break or this afternoon. So thank you.
Thank you, Eduardo, for presenting us this amazing beamline that you can do almost everything.
Yeah.
Maybe the question is what you cannot do it.
Exactly.
Okay, any question from the audience?